Shall I start?
Yes, you may go on now.
So, welcome to the first workshop of third workshop of Continuum. And in this workshop, we will learn about filter design. So, so before we move on to filter design, we will first see some terms about filter design. And first up is transfer function. So what is transfer function is it is the ratio of Laplace transform of an output and Laplace transform of the input. Suppose if there is a circuit over here and you consider the current voltage across voltage here as the input and the voltage over here as the output, then the Laplace transform of this output and by Laplace transform of this input it gives us the transfer function g of s, and you can represent the output as y of s and x of s is the input. So the polynomials, and we have seen that in the first workshop that the Laplace transform mostly it will be in polynomials. So the numerator will be a polynomial of m order and the denominator will be a polynomial of nth order. And we will say we will say a transfer function is a proper transfer function when n is greater than m. If n is greater than m, then we say the transfer function is proper, or else we say that improper transfer function. And so, what does transfer function actually tell us? It tells us about the stability of the system. We'll see this in a minute. And it tells us about the time domain and frequency domain of the system, the characteristics like given a transfer function, then you can plot the actual time domain graph of the voltage or the from that. And it also tells us about the response. You see, response is just for a given input, what will be the output. So from the transfer function formula itself, transfer function is the ratio of output by input. So if you take input to the other side, then you will get input into transfer function will give us the output. So if you know the transfer function for any input, you can calculate the output. So these are the three main things that transfer function tells us about. So now we'll see what is how it will show us the stability of the system. Here we seen here it is given as an example transfer function y of s is equal to y of x by x of s, and the roots of the polynomial in the denominator are called as poles. Like suppose if there is a normal polynomial fraction, then the roots in the numerator are called zeros, because if you substitute that number in place of s, then you will get zero as the output. Like, so, and if you substitute that number in place, the pole in place of s in the denominator, then you will get this denominator as zeros. Total transfer function will be infinity. So poles are the roots of the denominator and zeros are the roots of the numerator. And the system order is always equal to poles. Here it is nth order system. The number of poles is equal to the order of the system. And the next is, suppose this is a 3D plot. This axis is the transfer function L, that is the Laplace of the transfer function. Laplace equal x by s, x, y by x, you can say, this axis. And the other axis is the s plane, the other two axis. So this is the sigma plane and this is the j omega plane. So when this sigma plus j omega is the pole of the function, then the Laplace of that function will be infinity, undefined, and zeros can be found somewhere in between. So this is how a 3D representation of the transfer function looks like with a single pole. So here this transfer function reaches infinity only once. So that's why this is a single pole system or first order system, you can say. And so now coming back to the stability. So we can plot the poles and zeros in the S plane of the system. Remember, S is sigma plus j omega. S is a complex number. So this is the sigma axis. This is the 2D representation. This is the sigma axis. X-axis is the sigma axis, and y-axis is the j omega axis. And this whole side we call it as left hand plane, and this whole side we call it as right hand plane. So the if the poles, and we represent poles as x crosses, and we present zeros as zeros, like they are dots. So if all the poles of the system lie in the left hand plane, so if every pole lies over here, then this system is said to be stable. If all poles, if there is a single pole that lies in the right hand plane, then the system is said to be unstable. And if there are a few poles that lie exactly on this imaginary axis, j omega axis, then the system is said to be marginally stable. So this is how we see whether the system is stable or unstable given a transfer function of the system. And we will see an example. Suppose the transfer function g of s is 8 by 2 of 2s plus 5. Here there are no zeros because 8 you can't get a 0 in the numerator. And the pole of the function would be minus 5 by 2. So the pole of the function would be minus 5 by 2. And here the denominator order is 1, s power 1. And here the denominator order is 0, numerator order is 0, s power 0. So the numerator denominator order is greater than numerator. So this is a proper transfer function. And the order of this function is 1 because the number of poles is 1. And the pole here is minus 5 by 2, and minus 5 by 2 is minus 2.5, and it lies in the left hand of this axis. So this system is said to be stable because the only pole that it has lies in the left hand plane. If suppose here it is minus 2s minus 5, then the pole would be plus 5 by 2. Then this pole lies over here. Then then the system is said to be unstable. If there is a single pole, even a single pole that lies in the right hand plane, then the system is said to be unstable. Okay. Next, we will see how the time domain and frequency domain characteristics can be set from the transfer function itself. So suppose there is a there are two transfer functions. There are four transfer functions over here, and S1 and S1 conjugate. This S1 star represents S1 conjugate. That if S1 is A plus J into B, here J is the imaginary number, A plus JB, then S1 star would be A minus JB. S1 star would be the conjugate of S1. So here suppose there are these four transfer functions. One has S1 as S1 as the pole, and other has S2, and other has S3, and the other has S4. So the farther the pole is from origin in this direction, that means the farther the pole is, the less the magnitude of sigma, that is the real part of this pole, then the greater will be the decaying rate of that function. Suppose if here S4 and S2 you see, these two functions would be like this, but which decays faster? Like there can be a function which can decay like this, and the other function which will decay like this. So it will reach 0 first, this will reach 0 after a long time. So 4 is more farther away from the origin than S2. So S4 will decay faster. That means S4 will reach the constant, that is 0 or infinity steady state, faster than S2. So S2 will reach somewhere over here, and S4 will reach faster. And the farther the pole is from this sigma axis, that is the more the magnitude of j omega for the pole, the imaginary part of the pole, then the more will be the frequency. So suppose for S1 you see, S1 is farther from S1 is farther from the sigma axis than S3. So S1 will decay faster as well. You can see that S1 is also farther from the j omega axis as well. S1 is shorter from j omega axis, and S3 is farther from j omega axis. So the frequency for j omega axis would be more. that is S3's frequency would be more. So S3 would be like this, and S1's frequency is less, and also S1 decays slower because it is farther from this. Sorry, it is less from this S sigma axis. So S1's decay rate would be slow, and S3's decay rate would be faster. So that is what transfer function tells us. And now board plots. Board plots are simple graphs where we plot where the graph is y-axis, we plot the gain, and in the here we plot the gain in the y-axis, and in the x-axis we plot the time or any unit frequency. So in what is different in load plots is we plot gain in terms of decibels. So 1 decibel is equal to 20 into log a base 10. So a is here the actual gain, and gain in decibels is 20 log a. So that we plot in the y-axis, and in the x-axis as well. Each unit is called a decade. Suppose in a normal graph, each unit represents like this will be 1, this will be 2, this will be 3, like that, right? So for a load plot, what happens is this: if this is 1, then the next unit would be 10, and the next unit would be 100. So every unit would be 10 times the before unit. So that's why each unit is known as a decade. The step is known as decade. And this is what a board plot is. There are also other plots. Suppose here it is 20 decibels per decade. You see decade as 10 into 10 of this thing. And octave would be into 8 or into 16, into 8. So those are called board plots. And this is a single pole and zero pole board plots. So as you can see over here, this is known as a decade. Each unit is called decade. If here it is zero point 0.1 units, then here it would be 1 unit, and the next thing would be 10 units. So these are called board plots. And now we'll move on to filters. So first, what are filters? From the name itself, filters are something that filters out the input. Suppose if we have an input and versus frequency as like this, and we want to filter out this part, this whole part, then the filter should give us this. And this for here it should be 0, and then from here over here it should go. So this is what a filter does. It filters out unnecessary things from the input. And there are basically we define filters from how they filter out the input, like what frequencies they filter out the input. So there are low pass filters. These filters allow all the low frequency inputs and eliminate all the high frequency inputs. And these and there are high pass filters. These filters are opposite to low pass filters. They allow high pass frequencies, and they stop all the low frequency ranges. And band pass filters, these allow only the specific frequency range from f1 to f2, if you say from f1 to f2, and they reject all the other frequency ranges. And band rejection is opposite to band pass. They reject from f1 to f2, allow all the other ranges, r minus f1 f2 range. So these are the board plots, suppose. And for the low pass filter, the gain would be till here, and we call a cutoff frequency somewhere in between. An ideal filter should give us a gain should be like this, and it should drop to 0. But practically, it is not possible. There still will be gain as the frequency gets higher, and finally at some frequency it will drop to 0, but it won't drop to 0 at the exact range itself. So we will define a cutoff frequency in between. So before that we say that it allows all frequency, and after that this gain is negligible, we will say. So these are the board plots. As you can see, low pass will allow only the frequency lesser than the cutoff frequency, and it will stop all the frequency greater than the cutoff frequency. And for high pass it is opposite. It will stop all the low frequency ranges, and the gain would be more for the high frequency ranges. And band pass will only allow this certain region to be effective, and band reject is opposite to band pass. It will allow the lower frequencies and the higher frequency, but it won't allow this range of frequencies. So now passive and active filters. What are passive filters is these filters, the gain is less than 1. So the gain will be always less than 1. So gain in decibels will always be negative because log of some less than 1 would be negative minus something. And they are mainly made up of R and C components, passive components, R, L, and C. No active components would be used. So R, L, and C are are known as passive components. And in active filters, the gain would be greater than 1. And they are also made up of RL and C. And in addition to RL and C, we use op amps over there. Op amps you have learnt in the previous workshop. So we won't go into much details now about op amps. So these are active and passive filters. Now first we will see passive filters, passive low pass filter. So passive low pass filters, the and we will first see the definition of a half power frequency. What is half power frequency? The half frequency is the frequency at which the power will be half of the original maximum value. So suppose, and it occurs at the 1 by root 2 times of the maximum value. So suppose if there is a voltage, then power is directly proportional to V square. You all know this. P is equal to V square upon R. So power is directly proportional to V square. So now when P is equal to P by 2, then what would be the voltage? Voltage would be V by root 2. So half power frequency occurs only when the original, here V is the input, not power. So the input is 1 by root 2 times the maximum value, only then the half power frequency occurs. So the frequency at which power is half is known as half power frequency. And you know the resonance frequency, it is the frequency at which the magnitude would be huge, like maximum, like this. This is the resonance frequency, omega naught. If this is the graph, then the frequency at which it is maximum is known as the resonance frequency. You might have studied this as L omega is equal to 1 by C omega, because in there R plus L minus C root over this Ri plus Li minus C XCXL. So here when this is 0, then the phase shift will also be 0 and this would be maximum. So that's why this is known as resonance frequency when the maximum of the magnitude occurs. So next, a low pass filter. Low pass filter is made from an RC filter, RC circuit. So this is a basic RC circuit. As you can see, there is an input, there is a resistor, there is a capacitor, and the output would be the voltage across the capacitor. VC would be output. So this is a low pass filter, and the cutoff frequency for a low pass filter is 70 at the frequency at which the output would be 70.7%. That is the 1 by root 2% of the input. So this is the cutoff frequency. As we have seen from the definition itself, it would be half power frequency is the cutoff frequency. So the power occurs half when the voltage would be 1 by root 2 times. So this VC V naught upon root 2 should be the cutoff, should be the voltage value at cutoff frequency. So why we are seeing that this RC circuit acts as filter? If you recall, then XC is equal to 1 by C omega, and this omega is equal to 2 pi F or F by 2 pi something. So 1 by C omega, this is inversely proportional to frequency. So if you substitute that over here, then you will get this as 1 by R C omega plus 1. So this is what you will get into V in. So while frequency increases, then this denominator increases. Then the whole value decreases. If frequency increases, then this whole value decreases. So like this, if as you move on with the frequency, then there will be a drop in the gain continuously, and finally it will reach some value where it is very less than V in and it is very negligible. So that is why we use RC circuit as a passive filter, because it as frequency increases, then the gain would decrease or output would decrease with frequency. So this is how it looks like. The gain board plot, gain versus frequency. Gain is constant, almost constant. till the cutoff frequency, and the after cutoff frequency, this whole part is negligible, and the slope of this is known as minus 20 decibel per decade. So because we are doing decibel per decade, because decade is the x-axis and decibels is the y-axis. So the slope will be always be in the ratio of decibel per decade. And these are the cutoff frequency and phase shift formulas. Well, of course, if there is a, as you can see, voltage across capacitor leads the voltage across, like, sorry, the current across the capacitor. So like that, there will always be a phase shift if you use a inductor or a capacitor. So these are the phase shift and the frequency, cutoff frequency formulas. Now we will also derive this. This is just a simple formula. 1 by 2 pi RC is the cutoff frequency of this circuit. And the phase shift would be tan inverse of 2 pi FRC. And here F is the frequency at which, suppose over here, then this F would be the F. And here the frequency is this much, and the phase shift would be somewhere around 30 or 30 degrees or something like that. So at cutoff frequency, the phase shift is minus 45 degrees, because this 2 pi omega RC, F would be 1 by 2 pi RC, so everything gets cancelled, so it would be minus tan inverse 1, so phi would be minus 45 degrees. And so now derivation of cutoff frequency. And for the cutoff frequency, we will take the mod of this thing. So we are not dealing with the phase shift now. We are just dealing with the magnitude of the gain. So V out by Vin is Xc by R plus Xc. So mod Xc, mod R plus Xc would be root over R square plus Xc square, because the voltage across the capacitor would be in this direction, and voltage across the resistor would be like this. And suppose if current is in this direction, you have seen this in phasors, and for an inductor it would be upwards. So here the resultant magnitude would be root over R square plus Xc square. So and the gain at which the cutoff frequency occurs is 1 by root 2. Just a second. So this 1 by root 2 will be equal to 1 by omega c. This 1 by omega c is the xc value. You all remember this, I guess. And upon substituting this and equating, you will get you will get finally omega. Omega is equal to 1 by rc. So omega is equal to 1 by 2 pi into f. So fc would be 1 by 2 pi into rc. You know, omega is equal to 2 pi f. So f would be 1 by 2 pi into omega. So that would be, so cutoff frequency would be 1 by 2 pi RC. And next for the phase shift derivation, similarly, in here we have to mod. So if you don't take mod, you need to consider the direction, the phase shift of this thing. So we won't be taking mod over here. So xc would be j upon omega c. Here j, because the voltage across this would be in the bottom direction, and this would be in the direction. So the angle is 90 degrees. So you can see this is j upon omega c. This j, you can represent it as minus 90 degrees into j. So if you substitute this, you will still get, this is cos theta plus sine theta. So here angle is 90 degrees, so theta is equal to 90 degrees. So cos theta would be 0 and j sin theta would be j. So it is j upon omega c. So, and upon solving, simplifying this, you will finally get sigma phi is equal to minus tan inverse of omega rc. So omega is equal to 2 pi f. So minus tan inverse of 2 pi f rc. Here, what we did is, for any complex number, suppose if V out by Vn is equal to 1 by alpha plus j into omega rc by alpha, this you can write as x plus some j into y. So this x plus j into y, the angle between x and y, that is what we are finding, right? So the angle would be tan inverse of minus tan inverse of y upon x. So this would be the angle. So the same thing if you use for a complex number, you will get the phase difference. So and now a few regions. Just a second. Yeah. So pass band is known as this band, the range of frequency that is before the cutoff frequency. That is the range of frequency where the gain is actually significant. So and this is usually less than minus 3 decibels. And the transition region is the region where the gain decreases, falls off. There will be a decay in the gain. This whole region is the transition region, and the stop band region is the region where the gain is completely insignificant for us. So this is very close to zero. Here the gain is very close to zero. And cutoff frequency is the frequency at which the gain would be 1 by root 2 times or 70%, 70.7%. So these are the basic terminologies. You can refer to this diagram as well. And next to a high pass filter. So for a high pass filter, what we do is everything will be the same. Cutoff frequency will also be 1 by root 2 times when the gain is 1 by root 2 times. And we just inverse R and C. For a low pass filter, here there was R and here there was C. So for a high pass filter, what we are doing is we are inverting R and C. So what happens over here? So V out would be VR. So V out would be R upon R plus XC. So XC again is 1 by omega C. And if you substitute this, you will get R into omega C upon R omega C plus 1 would be this gain. So here as omega increases, both numerator and denominator decrease. So, but numerator, there will be significant increases in the numerator as well. So from this, you can say that as as low is this thing, then the numerator will decrease and the gain would be very less as frequency decreases. So here the it is directly proportional to frequency. Gain is directly proportional to frequency. So this is how the board plot for a frequency for a active filter looks like. Sorry, high pass filter looks like. So cutoff frequency occurs at minus 3 decibels, that is at 1 by root 2 times. The gain would be 1 by root 2, normal gain. So the gain in decibels would be almost minus 3. And this slope will always be minus 20 for a filter. We'll discuss this later. And this will be the pass band. This is exactly opposite to what we saw in the low pass filter. And the formulas remain the same. You can derive these formulas exactly like we did for the low pass filter. You can try them out yourself. So a cutoff frequency would be 1 by 2 pi RC and the phase shift would be minus tan inverse of 1 by 2 pi FRC. Here the phase shift is reversing. Just for that there won't be 1 by, it would be 2 pi FRC for a low pass filter, and for here it is 1 by 2 pi FRC. So next up is band pass filter. So if you connect a low pass filter and a high pass filter, suppose if there is a filter that is like this and there is a filter that is like this, then you will get a band pass filter. So here in this diagram that I have drawn, if this is the low pass filter and this is the high pass filter. So for a high pass filter, as we have seen, the frequency cutoff frequency is greater than that of a low pass filter. So here now what happens? I'll draw it bigger over here. So this is a low pass filter and this is the high pass filter. the high pass frequency cutoff is greater than low pass cutoff frequency. So now what happens? But this here we are getting the reverse of what we want. So what should be the ideal case is, first the the cutoff frequency of the high pass filter should be more than that of the low pass filter. So if the cutoff frequency for a high pass filter is lower than that, then it will allow all these things. And for the if the cutoff frequency of the low pass filter is more than that, then it will stop all these things. So finally we will get only this band of frequency to be allowing through the filter, passing through the filter. So for a band pass filter, the cutoff frequency of a high pass filter must be always be less than cutoff frequency of the low pass filter. And they are connected in series. So as you can see, the first circuit is a low pass filter and the second circuit is a high pass filter. R and C are reversed. So here, even here, the frequencies remain the same. 1 by 2 pi R1 C1 would be the cutoff frequency of the low pass filter, and 1 by 2 pi R2 C2 would be the cutoff frequency of the high pass filter. And bandwidth is defined as the difference between the upper critical frequency and the lower critical frequency. So that is over here the bandwidth would be this minus this. The range where the gain would be significant is called bandwidth, or where the filter allows the input to pass through is called bandwidth. And the center frequency is 1 by root over FL into FH. So this is the center frequency. The center frequency would be over here. And the FL would be the lower cutoff frequency, and the FH would be the higher cutoff frequency. So the bandwidth would be FL minus FH minus FL. And here FL, this is the cutoff frequency of the high pass filter. As you can see, but this is the high pass filter. And FH is the cutoff frequency of the low pass filter. So this is low pass filter. And the cutoff frequency formulas remain the same. And now a band stop filter. So what happens for a band stop filter? We have seen that if the cutoff frequency of the high, it is not just simply that here we are saying the cutoff frequency for a band pass filter, cutoff frequency is high. Half a high pass filter is more than that, should be less than that of low pass filter. If we reverse this thing, then what happens? So first, the cutoff frequency of a low pass filter is low. Suppose if there is a signal that is going more than that of the low pass filter, then it won't even be transmitted from the low pass filter itself. So there won't be any change if it is not at all transmitted from the low pass filter. So it will still be zero. And if there is some low, if you even reverse this circuit, first you put a high pass filter and then a low pass filter, even then it won't happen. So this, for a band stop filter to be made, then you need to replace the series configuration of low pass and high pass filter to the parallel configuration, because in parallel, first, if there is a filter, if there is a frequency that is more than high pass, then it won't pass through this. Suppose this is high pass filter and this is the low pass filter. So if there is a frequency that is greater than high pass filter, then it won't pass through. Sorry, that is, there is a frequency that is lower than a high pass filter, then it pass through this. And if there is a frequency that is greater than the low pass filter, then it won't pass through this, but it will pass through this because high pass filter allow all the high frequency ranges. So finally, we'll get only the one of these two things, but not both. So that's why there will be a empty region in between, and all other regions would be pass band. So these are all band passes, pass bands, and this is the transition region. The formulas will still be the same. So this is how you construct a low pass, band stop filter. We'll configure the high pass and low pass filters in parallel configuration, And finally, this amplifier, we'll see about this amplifier later on. So the low pass filter would have this board plot, and the high pass filter would have this board plot. And if you combine these both, you'll get this the band stop board plot in parallel. Remember, for a band pass filter, it needs to be in series. For a band stop filter, it needs to be parallel. So next, cascading. Cascading simply means adding or joining two circuits. So simple example is the if you attach two RC circuits. So two layer both are low pass circuits because C is over here. The output is through the capacitor itself. So if you add or join two low pass circuits, this is a first order low pass circuit and this is a second order. This is also a first order low pass circuit. So if you add both these low pass circuits, what happens is this will become a second order low pass circuit. And the frequency cutoff frequency for this also changes. And it would be root over 2 pi 1 by 2 pi root over r1 c1 into r2 c2. So instead of 2 pi rc, we have got 2 pi into root over r1 c1 into r2 c2. So what happens? What is the use of cascading over here? So as you can see, cutoff frequency decreases. That is one use, and the other use would be the roll off increases. So we have seen that suppose if this is the board plot for a low pass filter, this the board plot would be somewhat like this. So this slope is known as roll off rate. So for an ideal filter, this should be like this. It should be as vertical as possible. So we are talking about the magnitude. It will always be negative this slope. So rollout rate increases means this magnitude will increase. That means this whole thing increase because negative of that would decrease. So what happens if roll off rate increases means the slope would be like this. So it will more and more towards this vertical. So it becomes more and more close to vertical, and as it and it becomes more and more ideal. So that is what we want. We don't want unnecessary things to be more. So next are active filters. So we have seen passive filters. What are passive filters? They are constructed. So why we need active filters if we already have passive filters? Here the gain can be altered to our wish. So in the passive filters, we don't know that how much the gain we will obtain because gain will always be less because this gain and this for any series elements you can see that the output across this voltages the voltage across these passive elements would always be less than the voltage across this force. So we can we can increase the gain as much as we want in active filters. And there is also one more problem, loading problem. So what is loading problem is here, suppose while cascading or while if you are cascading a low pass and a high pass filter, that is two band pass filters. So the output would be across these capacitors, right? So we take the whole output across these capacitors only. But there is also this whole circuit as well. If you cascade, what happens to this circuit? We won't be taking this circuit into consideration over there. We will be just taking some assumptions and we'll be getting close to the answer. But for us, while cascading, this this resistance, the equivalent resistance of this second circuit should be as high as possible. It should be close to infinity or very high compared to this circuit. Or else more current will also flow across this circuit and there will be less current across this circuit. And final output gain would reduce because the current across this reduces, so voltage will also reduce. We don't want that. So for that, that is called loading problem. And to also solve that problem, we use active filters. And these are also economical as well, effective as well. So we'll see the comparison between passive and the ideal filter. So for an ideal low pass filter, it should just drop to zero after cutoff frequency. This is the cutoff frequency, and it should just drop to zero. There shouldn't be any transition range at all. And for practically, there will be a transition range, and it won't directly drop to zero. And somewhere in between, we will get a cutoff frequency. So, and the reverse would be for the high pass filter. So it should be zero till the cutoff frequency, and after the cutoff frequency, it should just directly shift to one or shift to the significant gain. And there shouldn't be any transition region here as well. So this is how the practical port plot of a high pass filter looks like. So the next would be the band pass filter. So for the band pass filter, this is a practical band pass filter. If you take the ideal band pass filter, it should be somewhat like this. So it should transmit all the frequencies between the cutoff frequencies, and it should just reject all these frequencies. So we have already seen these all things before in passive filters. So now quality factor. This is a new definition. Quality factor is equal to F naught upon band. F naught is the center frequency. So for a band pass filter, F naught, this is the center frequency, and bandwidth would be FC1 minus FC2. So this quality factor is defined as F naught upon bandwidth. So the higher the quality factor, the lower the bandwidth, the narrower the band would be. So we will say if the quality factor is greater than 10, then the band is it is a narrow band, and if it is less than 10, the band then it is a wide band. And quality factor is also defined as 1 upon damping factor. We'll see this damping. What is this damping factor? So these are the main definitions. And next, frequency response characteristics. So if suppose there is a filter, then it is not always possible to get a gain like this. The board plot won't be always like this. There may be ripples in between, or it can just start directly going like this. So we will see the three main filter response characteristics. The first one is Butterworth characteristics. Then we have Chepev characteristics. Then we have Bessel characteristics. So first, Butterworth characteristic. In Butterworth characteristics, what happens is the gain would be constant. It would be slope. It would be a constant till some value, and then it will start decreasing. The rollout rate for a Butterworth characteristics for a single pole Butterworth characteristic would be minus 20 decade per pole. So decade per pole is single pole system, it would be minus 20. For a two pole system, it would be minus 40, like that. So as the poles increases, this roll off rate decreases. That means this graph would be more tending towards vertical. So this is Butterworth characteristics. The gain would be almost horizontal most of the time, and then it will start decreasing at a roll off rate of minus 20 decibel per decade. And next are Chebyshev characteristics, and over here there will be ripples in the gain. So Butterworth is as horizontal line, and for a Chebyshev it would be a ripples. So this has less, and this Chebyshev complex characteristics occurs when there are very less poles and there will be ripples in the gain. So that's why even having more poles also solves us this problem of getting a constant gain across this whole filter frequency ranges. So this is Chebyshev characteristics, and next the Bessel characteristics. So whatever characteristics would be a horizontal line, and Bessel characteristics would just start decaying before Butterworth itself. So it will be constant for a very little time, and it will start decaying. So and Bessel characteristics are used in pulse waveforms and distorting shape of waveform. So these are the three main characteristics, filter response characteristics. And next we move on to the active filter. So filters are just the transfer function of the system. So the transfer function is the filter basically. So because h of s is equal to out upon v in, this is the transfer function, and this is the gain as well. So this is the filter itself. The transfer function is the filter itself. And the order of the transfer function is equal to the order of the filter. And how do we calculate the order of the transfer function? That is equal to the number of poles of the transfer function. So suppose if we take a single pole passive low pass filter, we have seen at the starting of the workshop. Here transfer function gain V out by upon V in would be C upon XC plus R. So if you substitute XC as 1 by SC, we will get this whole transfer function is equal to 1 upon 1 plus SRC. So here there is only one pole. So the order of this transfer function is 1. So the order of the filter would be 1. So this is a single pole passive low pass filter. We call it as single pole filter because there is only one pole. So as poles increases, the roll off rate decreases, and the more the poles, the better will be the filter inclined towards the ideal practices. So and the damping factor of the filter. So basically, an active filter consists of an RC circuit. This is a parallel. This is a passive filter, and then an amplifier. So why do we use an amplifier or an op amp? So this op amp is used to get our desired gain instead of just a gain less than 1. So with this op amp, we will get a gain that is greater than 1 or any gain that is our desirable gain. So the damping and this op amp is also connected in a non-inverting manner. You might have you should have studied this in the second workshop. So this op amp will be connected in a non-inverting manner. So this ratio of R1 upon R2, 2 minus R1 upon R2 will give us the damping factor. And 1 by damping factor would give us Q, quality factor, is equal to 1 upon this. So the less the damping factor, the better the quality factor, and the better would be the the filter performance. And we'll see what is an active low pass filter. So active low pass filter is just connecting a passive low pass filter to an op amp in non-inverting configuration. So all the filter characteristics, everything that it needs to be filtered out will be filtered in this passive component, RC circuit itself. And this op amp will amplify the output as much as we want. So the board plot won't change. The gain can be anything, how much ever we use the amplification for. And it will be same as the passive filter itself. And this roll off rate would be minus 20 decibel per decade. And the number as roll off rate decreases, number of poles will increase. That is, if number of poles is increasing, then the roll off rate would decrease. So everything for a passive, as I told you earlier, all the filtering does occur at the passive circuit itself. So all the formulas in the passive low pass filters would actually be true for active low pass filters as well. So FC cutoff frequency would be 2 pi 1 by 2 pi RC, and here the gain of the in we have seen this in the previous workshop for a gain of the non-inverting op amp would be 1 plus R1 upon R2. So the gain of the op amp would be 1 plus R1 upon R2. So this is how an active filter is converted. A passive filter is first passive circuit is made, and then this passive circuit, the output of this first there is an input V in, and this passive filter, that input is passed through this passive filter, and we will get an output Vi, and Vi is the input for this non-inverting op amp, and finally we'll get the output V out. This is the output, and this final output is that output of the active filter. So this whole passive filter plus a non-inverting op amp would give us an active filter. So these are basically the active filters. So everything true for the passive filter is also true for the active filter. And the advantage of an active filter is we can modify the gain as much as we want, and there won't be any loading problem as well, because the resistance inside the op amp is too high. So there won't be any loading problem, and all the current would be across this, and the voltage would be across only the passive filter as well. So it solves almost all our problems significantly. So the roll-off rate now, as number of poles increases, the roll-off rate decreases by 20 decibel per second. So this is a single pole, minus 20 decibel per decade is the single pole, and then a minus 40 would be for a two pole, and then the minus 60 for a three pole. So minus 80 for a four pole and minus 100 for a fifth pole. So everything will be there, and finally the more the number of poles, the closer it will be vertically, and the closer it will be to an ideal filter. So that's why we use more and more poles to get close to that ideal filter we want. And this is how cascading of this active filters is. This whole thing is a one filter, one single pole filter, and this is another single pole filter, and this is another single pole filter. But here we are using op amps too many times. So can we do this in a better efficient way? We'll see that this is the three order because there are single pole systems. This is basically the third order active low pass filter. So next we will see silent key low pass filter. Here what we are seeing is there is also a feedback across the capacitor through a capacitor. So we won't be going too much into this circuit. It will be a bit complex as well. So here there are two RC circuits, this RC circuit and this RC circuit. So there are two RC circuits over here. So this will two pole filter, and we are using only a single op amp. So if you see over here, if you take out this thing, then this whole thing is a two pole op amp, two pole active filter. But we are using op amp two times. So we are being more economical here and more effective as well. This here we use op amp only a single time, and we are giving a feedback through a capacitor to the output. So this is a silent key low pass filter. There are two RC circuits, so this is a two pole filter. And the formula for the cutoff frequency for this is 1 by 2 pi root over RA/RB into CA/CB. This is this exact same formula while cascading as well. So this is exactly similar to cascading. Nothing changes over here as well. And if you take all R equal and all C are equal, you will get FC is equal to 1 by 2 pi RC. So while building a filter, you don't want many complications across the filter while calculating the cutoff frequencies and all. So while building any filter, while designing a filter, we generally take all RAs, all resistor values are equal, and all capacitor values are equal across all the RC circuits in the filter. For calculation and complication, to reduce the calculations and complications in the filter, we take everything as equal. So it would just be simply like a low pass filter as well, 1 by 2 pi RC. And cascading, here you see the three pole filter is obtained with just two op amps. This is a two pole filter, silent pass filter, two pole, and this is a single pole filter. So cascading these two would give us to three pole low pass filter. You may say that what if we put another over here and another feedback? That won't work because that would be really complicated circuit and we don't know what the output would be. There might be a lot of complications like that, so we don't use more than one feedback here. So this is how cascading of silent key filters happens. And then a four pole filter would be two silent key filters. So this is a two pole filter and this is also a two pole filter, and cascading would give us four pole filter. And next is the active high pass filter. It is exactly the same as the low pass filter, except here R and C values are reversed. So in a low pass filter, here there was R and here there was C. Here they are just changed. So everything remains the same. The cutoff frequency would be 1 by 2 by RC, and the gain would also be 1 by R1 upon R2. And the cascading would also be the same as well. So next, the silent key high pass filter. Even here, everything remains same except the R and C are reversed. Even here as well, there are two RC circuits, RA and RCA, and CB and RB. So these two circuits form a two passive low pass filters, and the amplifier op amp forms the active filter. So when here the roll off rate decreases as the number of poles increases. So for a low pass filter, the roll off rate is like this. Then for a pass two pole filter, the roll off rate would be like this, and it will get closer to the vertical line as we increase the poles. So even here the formula remains the same, 1 by 2 pi upon root 2 pi into root RA RB RCA CB. So we take all resistors are equal and our capacitors are equal, then we'll get 1 by 2 pi RC. And next would be cascading of these filters. So cascading, just joining all these circuits, you'll get a 6-pole filter. All these are 3 2-pole silent key low pass high passers, and cascading all this would give us a 6-pole high pass filter. Next, active bandpass filters. So discussed earlier, bandpass filters are obtained by series combination of a high pass filter and a low pass filter. And the cutoff frequency of the high pass filter must be less than the cutoff frequency of the low pass filter. So here these are two silent key high pass filter and silent key low pass filter. So these are two pole high pass filters. So the roll off rate would be -40. So these are all the band pass frequency response characteristics. We have seen this earlier. They're exactly the same. And these formulas also don't change. And now a multiple band pass filter. So here what we are doing is similar to a silent key filter. We have added another feedback through a resistor instead of a capacitor. We have added another feedback through a resistor. So what happens is this RC circuit is actually in parallel to this RC circuit. So this acts as a band pass filter, and the cut center frequency would be f naught is equal to 2 pi into 1 by 2 pi upon root R1 and R3 are parallel here. R1 and R3 here are parallel because we are adding another back through resistor. There will be a parallel thing over here into R2 into C1 C2. So if you take C1 C2 and C all are equal, then we will get a center frequency as this. Remember, this is a center frequency, not the cutoff frequencies, because for a band pass filter, cutoff frequencies would be that of the low pass and high pass filters, but the center frequency would be calculated here because that would be actually of the band pass filter itself. And if you know the quality factor of the filter and the gain of the filter, then you can find the resistor values of how much you need to put to obtain the desired quality factor. So, and the maximum gain occurs at R2 upon 2R1. And next are band stop filters. So for a band stop filter, this is a multiple feedback band stop filter. So the active and the low pass and high pass filter needs to be parallel. So this would give us a band stop filter. If that is in series, then it would give us a band pass filter. So here this you can remember this circuit. There are there is another resistor over here R4 as well. So this is a multiple feedback band stop filter. And next are frequency response measurements. So measuring these frequency responses can be performed by the graphs. Like you can plot each and every point for some frequencies ranges, and you can plot the graph of these both plots. And next is the summary. You can go through this summary by yourself. So thank you. This is the third workshop of the Continuum, and this is the last theoretical workshop. In the next workshop, we will see about ORCAD and how you can use ORCAD. So if you have any doubts, you